So yeah, without wasting much time, let's jump into it quickly. Let me quickly introduce Shannon's expansion theorem to you. So imagine you have a n+1 variable Boolean function, from 0 to n, and that function can essentially be decomposed into two parts. The first part assumes that xn is 0 and ANDs it with xn bar. The second part assumes that xn is 1 and ANDs it with xn, right? If you really look in the circuit diagram of it, essentially how it looks like is you have this mux sitting here in green right here, and you are giving two inputs into it. One is a function value one is a function value that has been computed with xn equal to 0, and another is a function value that has been computed with xn equal to 1. And then based on the value of xn, that is if it's 0 or 1, you choose which function value to pass as the final function value. It's pretty simple. It's like compute function f assuming xn is 0, compute function f assuming xn is 1, and then based on the value of xn, forward the result which is computed with the accurate value of xn, right? So if our xn was 1, then this result here will be forwarded to the output. So I think that's pretty straightforward, right? Now, let's quickly look at the real-life application of Shannon's expansion theorem. Now, we're going to look at ripple adders versus carry select adders. And if you don't remember ripple adder or carry select adders, that's fine. I'll give you a quick overview of ripple adder first. And then we'll try to synthesize carry select adders out of the ripple adders using the Shannon's expansion theorem. Right? Okay, let's quickly jump into it. So, the ripple adders are essentially made of a chain of full adders, right? Connected all the way to the end. Now, this ripple adder is essentially adding a n-bit operand A with another n-bit operand B to compute a result, a n-bit result, right, along with the output carry bit, right? And there's an input carry bit as well. I don't want to represent this in the notations because it'll get really complicated, so I'm trying to keep it simple. But what I'm trying to say is, like, you're adding two n-bit values here to get an n-bit sum value, which you can see we have computed here, right? And you can also give an input carry to it, and this ripple addition, starting from LSB adder to the MSB adder, will eventually generate the output carry Cn, right? Now, if you don't remember what full adder is, let me give you a quick overview of its truth table. So you can see a full adder takes three inputs, a carry input and two operand inputs. These three single bit inputs are then added to compute the sum and carry, right? So if you add 0, 0, 0, sum is 0, carry is 0. If you add 0, 0, 1, the sum is 1, carry is 0. If you add 0, 1, 1, the result is going to be 1 plus 1, which is 2, right? So 2 is represented as 1, 0 in binary, right? Which means sum is 0 and this 1 is the carry, right? So you can see sum is 0, 1 is carry. Similarly, 1, 1, 1 is essentially 3. 3 is represented as 1, 1 in binary. So sum is 1 and carry is 1, right? Now let's move forward and let's look at the ripple carry addition. So as you can see, the inputs are fed, the carry input is being fed at this one side. Let me use a different marker. is being fed at one side and you're getting a carry output at the other side, while the sums are being computed as the carry is rippling through this full adder chain, right? Now, to give an example, let's imagine you have to add these two numbers, 1111, 1011, right? So how will you do the addition? So 1 plus 1 is essentially 2. So 0 and 1 carry is 1. And now 1 plus 1 plus 1 becomes 3, right? And 1 plus 1 plus 0 is 2 again. So this, right? And 1 plus 1 plus 1 is 3. So 3. And this guy is my Cn, or carry out. And the Cin was essentially 0. So in this particular example, my Cin was 0, my C out or Cn, whatever you want to call it, well, in this case, Cn is essentially C4, right? Because there are only 4 full adders sitting here. C4 is 1, and S0 is 0. My God, that's a very big marker. I want to reduce the size of it. Yep. S0 is 0, S1 is 1, S2 is 0, and S3 is 1, right? So that's what we're seeing over here. So I think with this example, you kind of see how the carry is actually rippling, right? From here to here to here till here. And each of these essentially stands for, each column here stands for a full adder, right? And these are the sum, S0, S1, and this is my Cn or C4. Let's call it C4 because N over here is 4, right? C4. So now let's imagine that the time taken by a full adder to compute the sum or carry, right? So this is your full adder, right? The time it takes for it to compute the sum bit and the output carry bit is 10 nanoseconds. What does that mean? It means that the delay from all the inputs to sum is 10 nanoseconds, and the delay from all the inputs to carry is 10 nanoseconds. Now, there's some nuance to this. I'm not going to get into that because I'll just make the lecture a bit more complicated. So let's assume that the delay from all the inputs to each of the output is 10 nanoseconds. That's kind of what we mean over here. We'll get into the nitty-gritties of this statement a little later in the series, but let's just stick with this for now. So, okay, this is not clear. Let me get this clear. So, what I mean here is that the time it takes to compute S0 is 10 nanoseconds, right? Obviously, because the delay of a full adder is 10 nanoseconds from all the inputs, right? From all the inputs. So the time it takes to compute S0 is going to be 10 nanoseconds, and the time it takes to compute this carry out is also 10 nanoseconds. So, which is what I've written here. The time it takes to compute S0 is 10 nanoseconds, right? The time that it takes, the time that the ripple adder takes to compute S1 is going to be 10 plus 10, which is essentially 20 nanoseconds. Why? Why is that? Because of what we are saying is that the time it takes to compute this carry out bit from right from the time when these inputs have been fed in is 10 nanoseconds, right? So this delay is 10 nanoseconds. And also the time it takes to compute full adder, this S1, since A1, B1, and this carry has been fed in, is also 10 nanoseconds. So the total delay, that is starting from C0, feeding in C0, all the way to computing S1, is going to be 10 plus 10, which equals 20 nanoseconds, right? Right? So that's what we are saying here, that the time to compute S1 is 20 nanoseconds. Similarly, if you want to compute Sn minus 1, which is after n full adder stages, right? After n full addition stages, then that becomes n times 10 nanoseconds. And the time to compute Cn, which is the carry out of the nth full adder, right? Which is the carry out of nth full adder, that is also going to be n times 10 nanoseconds, right? Now, if say our n is 100, that is, we have 100 full adders, then the time to compute Cn is basically 100 times 10 nanoseconds, which is 1 microsecond, right? Or 1000 nanoseconds, whatever you want to call it. Note that this is also the delay of entire ripple adder to compute all its outputs, right? Because by the time 1 microsecond has passed, after all the inputs have been deposited and 1 microsecond has passed, all these values have been computed, because this will be the final value that this adder chain will compute. And by the time it starts computing this, these values have already been computed, because it takes lesser time to compute this than to compute Sn minus 1, right? Because the delay keeps adding down the chain. Okay, now what we are interested is in is to make this addition operation faster. And we are going to ask that, is there a way that we can make this addition faster? Can we do that? Now, if let's say we start with a naive approach, a fantasy-based approach of wanting to parallelize this adder right here. Let's say I want to divide my entire ripple adder into 2 parts, and I want these 2 parts to work in parallel. This part I'll call my MSB adder, and this part I'll call my LSB adder. And I want the MSB and LSB adder to compute in parallel, right? And if they compute the sum values and the carry value in parallel, then since my total delay of this ripple adder was 1000 nanoseconds, then if they work in parallel, then the time for the parallelized adder will become 1000 divided by 2, which is 500 nanoseconds, right? Because these both will be now working in parallel. We are trying to find a design which can make these 2 adders work in parallel so that the effective time halves, right? And if it halves, well, the logic becomes a lot more faster. So we are trying to investigate if we can do that, right? So if you see these orange boxes here, the MSB adder, this MSB adder is essentially this, and this LSB adder is essentially this. I've just represented them as boxes because it's just more easy to visualize than having me drawing full adder chain every now and then. So you can see that this MSB adder is getting Cn by 2 as its input, right? Just like here, Cn by 2 is the input of the MSB adder. and LSB adder is getting C0 as this input, which is the input over here. And there are other inputs which are A0, B0, A1, B1, all the way to AN by 2, BN by 2 minus 1, which is what I've shown here as well, right? And the output this LSB adder produces is Cn by 2, which I've shown here. It's Cn by 2. And it also produces S0, S1, Sn by 2 minus 1. So we can see that it's producing it, right? Similarly, there's a one-on-one correlation between the inputs and the outputs of the MSB adder diagrams here and there, right? You can do a one-on-one mapping and you can see it. Maybe pause the video to just verify. Okay, now what we are seeing is that although we might have broken our adder into two parts, there's a dependency here, right? That this adder still expects a Cn by 2. The MSB adder expects a Cn by 2, which it's supposed to get out of the LSB adder, right? Now, what if we come up with a bit of a clever design, right? We could say that the outputs of MSB adder are a function of Cn by 2, not A0, it's actually AN by 2, BN by 2, AN by 2 plus 1, BN by 2 plus 1, and all the way to AN minus 1, BN minus 1, right? The outputs of MSB adder are a function of these variables, right? Let me frame this equation a bit more elegantly. I'll use a better marker. So O is equal to f of Cn by 2, An by 2, Bn by 2, all the way to An minus 1, Bn minus 1, right? This O is essentially the outputs of MSB adder. So now, if I were to use my Shannon's expansion theorem, right, what can we do here? What can we do? What we can do here is we can make O as, we can decompose this function f as Cn by 2 bar f of 0, An by 2, this 2 is only a denominator of n and not a, right? Because that's just an index. Bn by 2, a n minus 1, bn minus 1, right? Plus c n by 2, no bar, correct? F of 1, a n by 2, b n by 2, a n minus 1, b n minus 1. Okay, awesome. So what that means is that we can run, now we can basically run the MSB adder, which is this guy, with this assumption. We can assume that the incoming carry into the MSB adder is 0 and compute all the outputs of it, right? Let's call it O1. And we can assume that the incoming carry to the MSB adder is 1 and compute all the outputs of it, which we call O2. And then O essentially becomes a muxed version of O1 and O2, depending on the value of Cn by 2. Now, I'm sorry if this notation is getting confusing. We'll clear this up. What is O1? What is O2? what is what, right? Let's make this simpler. Let's say that we want to compute Cn. We want to compute Cn, right? Cn, because it's an output of the MSB adder, is a function of Cn by 2. It's a function of An2, Bn2, n2 plus 1, bn2 plus 1, minus 1, minus 1, right? An minus 1, bn minus 1, Sn minus 1. These are the outputs. Sorry, these are the outputs. And we are interested in computing each of these outputs depending on the inputs, right? So what we are saying here is that we can compute Cn as a muxed version of two MSB adders running in parallel. With one MSB adder getting a carry input of 0 and the other MSB adder getting a carry input of 1, and they both will get the exact same An by 2, Bn by 2, right? All the way to An minus 1, Bn minus 1, exact same things. So depending on the value of Cn by 2, which will be computed by my LSB adder, right? I will multiplex which carry out goes out as the final carry out. Now this is interesting because essentially what I've done is I'm running my LSB adder in parallel. My LSB adder is running in parallel over here. It's getting a Cn, it's getting A0, B0, it's producing S0, S1, Sn by 2 minus 1. It's also producing a Cn by 2, right? This guy is now running in parallel to this guy because these guys have no dependency, right? The MSB adders are already getting a pre-assumed or rather an assumed carry input of 0 and 1, and then depending on the value of Cn by 2, which the LSB adder will compute, that value will be used by this mux to tell what Cn actually goes out as my final Cn. The same multiplexing logic will also apply on the sum outputs of the MSB adder, and I'll show that like in a little bit, right? I'll not draw a very elaborate diagram, but I'll try to show it very quickly, right? You have these two MSB adders, right? MSB say 0, which is getting a 0 as carry input, and MSB 1, which is getting a 1 as carry input, right? MSB 0 is essentially this, MSB 1 is essentially this, right? They are computing Sn minus 1 and Sn by 2, right? They're both computing Sn minus 1, Sn by 2, right? But it's just that they are assuming different values of carry-ins. They both are also getting exact same values of A and B, right? A n by 2, B n by 2, right? Exact same thing. Same as this, same as the one that I've drawn here, right? This exact same thing that I've drawn here. So now what you do is that you're gonna have a mux sitting here, which is going to get this carry in, and based on the value of Cn by 2, which this LSB adder will produce, right? This value will be given here as well, and this value will be used to decide which of these two go out as my final Sn minus 1, right? So now what we are seeing is that I have this one LSB adder which is running in parallel to my MSB adders, right? And it's being used to compute, MSB adder is being used to compute the MSB sum bits, and it's also being used to compute the Cn bit, right? But the good thing is that now my adder has been divided into exact half. So if I were to draw a little bit of a, okay, so I quickly drew this, and if you see this, I have MSB adders over here, and I have an LSB adder here, right? MSB adders and LSB adder, and the LSB adders are computing the first n by 2 values of sum, and it's computing Cn by 2, and it's taking first n by 2 operands and C0 as the input. The MSB adders are computing the MSB n by 2 values of sum. It's computing a Cn, but now we have two copies of MSB adder. One is MSB adder 0, other is MSB adder 1. The MSB adder 0 takes 0 as Cn by 2, right? And the MSB adder 1 takes 1 as Cn by 2. And then depending on this actual value of Cn by 2, this gets routed here to compute the final Cn. And similarly, this actual value of Cn by 2 gets routed to these muxes on these sum bits to compute Sn minus 1 all the way to Sn by 2, which are the MSB n by 2 sum bits. So what you can see now is that if my ripple adder delay, which is TRA, was 1000 nanoseconds, because we have parallelized our adder, right? The delay of this parallelized adder has now become 1000 by 2, which is 500 nanoseconds, because we have essentially broken down our adder into MSB adder and an LSB adder, right? The trade-off here has been that we have to replicate, or rather create, two copies of MSB adders, because we need to compute two sets of values which are assuming Cn by 2 to be 0 and 1, right? So what has happened is that my area has gone up, by 1.5x times, because I have duplicated the MSB half, right? So it has gone 1.5x times, but my total delay has become half, right? So by increasing the area, I have reduced my logic delay, which means that my design has now become faster at the expense of more logic area. And this type of adder is what we call carry select adder, and I think it's called that because we are literally using a carry bit to select what goes out of these muxes, right? So it's called like a carry select adder. So as we can see, we introduced Shannon's theorem over here, and we wanted to explore the area and timing trade-offs using Shannon's theorem. And this example of ripple adders followed by the carry select adder is a pretty good illustration of the area delay trade-off in these adders. And if you are an RTL buff, just like myself, the modern synthesizers like DC or Genus, they already do this thing for you. If you increase the clock frequency, usually your combinational area increases because it's trying to do something similar to this. It's trying to create a more parallelized logic so that it takes lesser delay, which can meet your high clock frequency. Anyway, I hope you really enjoyed the lecture. Please let me know what you think about it. And if you have any questions about any of these things, please let me know in the comment section. Also, I have a question for you. What happens in this scenario to the power of the circuit? How does the power of carry select adder compare with the ripple adder? Okay, please let me know. Thank you.